Okay, this is the last video of this chapter, and we are going to apply the one-tail test framework to a real example. So, and these graphs are about the health coverage in the United States before and after the legislation of the Affordable Care Act in 2013, right? So, so as you see, like we are interested in the percentage of uninsured people before the legislation. Percentage was 13.6%, but after the legislation, it's 9.9%. But so we want to see if this is same as this or not. By the way, there is not enough actually. After the legislation, the data are much smaller. The sample is much smaller. So we would like to put the hypothesis test if this is the same as this number or just a random shock, right? Okay, so for simplicity in our example, I'm going to assume that simply 80% of people in the United States had health insurance before the legislation, right? And we want to test, and we don't observe what happens after the legislation. So we would like to test about the proportion of those insured after the legislation. Okay, and in this case, one thing I would like to assume here is, so the Affordable Care Act may have no impact on the coverage probability. However, I assume that negative impact is not possible. So either it has zero impact or positive impact. So that's competing hypothesis. But there is no negative side effect, right? That's what I'm going to use as an assumption in this testing. So I focus on this hypothesis. So the null hypothesis is no impact, and alternative is positive impact. So they are competing, right? So it's an upper tail test. So you are going to reject the null hypothesis of no impact if the observed percentage is significantly higher than 80%. That's an upper tail test. So rejection, remember, rejection happens on the upper side. Upper tail is where we reject. And again, and in a survey, so after the Affordable Care Act came into effect, you did a survey of 100 random people, and you find 86 of them had health insurance, right? So it looks like it's 86%. So it looks like slightly higher than you expected, but I'm not sure if that's statistically significant or not. So it could be just a random error or not significant. Another thing we have to think about here is that this random variable is binary again. So we have used the binary distribution structure several times in different contexts, and we are using it again here. And the main structure is the standard deviation. Standard deviation is implied by the mean probability. And in here, the null hypothesis 80% implies the standard deviation of 0.4. So if the null hypothesis was correct, then probability is 0.8. That means standard deviation is 0.4. So using this standard deviation, we can calculate the t-statistic first. T-statistic, what you observe, 86%. What you believe, 80%. Difference is standardized. And you get 1.5. So t-statistic is 1.5. Now then, think about the decision rule, you may use the t-statistic approach or p-value approach, and either way, determine if you can reject the null at the 5% significance level or not. Right? You need some algebra, and you need to find the threshold. Okay? So the answer is this. Say, so your t-statistic is 0.5, and in the t-statistic approach, you are going to reject if the t-statistic is too high. So because we are doing upper tail test, we reject on the upside. So you just need to set the threshold, and the threshold for 5% in one tail test is 1.64. That means your t-statistic is not large enough to reject the null hypothesis. So H null is not rejected. That means it seems that 86% is just a random error. So 6% increase was not significant. It was just it could be a random error. That's the conclusion. If you use the p-value approach, then you calculate the probability greater than the t-stat, right? Greater than 1.5, and you calculate this probability from Excel, then you get 6.681, which is greater than the significance level, so you don't reject the null hypothesis. Because we consider 5% significance level, and p-value is greater than that. So it's not, either way, the conclusion must be the same. Just do whatever you want. So there is nothing special. Just use in the binary distribution, the standard deviation is calculated in a specific way. Other than that, there is no difference. Okay, now let's use the critical value approach. So again, the critical value is only on the upside and rejected if the realized sample average is greater than the critical value. And if you use the 5% significance level, critical value will be calculated this way. So start from the hypothesis 80% plus 1.64, because 5% one tail, it's 1.64, top 5% value. And then margin of error will be calculated this way. So simple. The upper critical value is 86.56%. So you allow a margin of error of 6.56% point. That is quite a huge margin of error. And in this case, again, you cannot reject the null hypothesis because your critical value is higher than what you observe. So your observation is not greater than the critical value, so you don't reject the null hypothesis. Okay, the next step, we are going to use this critical value to calculate the error probabilities. So again, please do it by yourself. What is the type 1 error probability? All the hypotheses are the same, data are the same, significance level are the same. Just calculate the type 1 error probability. Okay, the answer is 5%. You don't need any algebra. So just type 1 error probability is the significance level. So they are the same thing. Always equals, again, I say that no matter what, whether it is two-tailed or one-tailed, no matter if it's binary distribution or not, always they are equal. But this is not easy. So now, suppose that actually the truth is that the coverage probability, coverage percentage, insurance coverage increased from 80% to 90% after the legislation. And then you had to reject the null hypothesis, but if you can't, then it is a type 2 error. What is the type 2 error probability in this case? If you assume this is the truth. And a hint, minor hint, is that 90% implies a standard error of 0.3. So there is no shortcut. The algebra is not simple. Okay. Okay, let me show you the answer. So we assume that the truth is 90% after the Affordable Care Act takes effect. And then it implies, using the binary random variable structure, it implies a standard deviation of 0.3, as I said. And you use these two parameters to standardize the normal distribution. So mean, standard deviation. You use these two numbers based on the assumed truth. And then you know how to calculate this. Standardize with those specific numbers. And then you get z smaller than minus 1.1466 to use the calculator. You get 12.5%, which is type 2 error probability. That means, like, even if the insurance coverage, healthy insurance coverage, increased from 80% to 90%, but you may not be able to see the difference from the data with this much probability. Quite high, right? So, and in other words, the power is about 87.5%. 87.5%, you can clearly detect there is a difference. There is a positive effect from the policy. Okay, so this is another example. This was the final example in this chapter. So we have finished chapter 10, and actually all the main basic inference methods are covered. So in the next chapter, we will start correlation coefficient and covariance, which is slightly different from what we do in these inference chapters. So, okay, have a nice week and see you next week. Bye bye.